Greeting, folks. My name is Daniel Parra Hensel, he, him, el, from the Arroyo Burro watershed in the Syuxtun village of the Chumash territory, also known as Santa Barbara, California, doing work within ecological justice, looking at the different links between the ecologies that sustain us, the water cycle, the carbon cycle, plants, earth, air, water, fire, life, all these things, and how that translates into our social justice organizing movements, and vice versa, how our organizing efforts, our social justice analysis can help inform our general environmental and ecological movements. I teach part-time at the local community college in Santa Barbara here in the environmental horticulture department. I do 2 permaculture design courses focused on community resilient design. Also the co-director of applied agroecology for a project called Somos Semillas, which is a food sovereignty garden project in the Lower West Side in Santa Barbara, looking to connect communities and families to the culturally relevant crops that we grew up eating and cultivating with our families, and connecting to food and place and soil and tending to land. I was one of the cohorts of the Training and Applied Agroecology program, TAAP, the cohort number 5. And today I will be presenting on water and soil conservation. The image you're looking at here is of a project in China called the Loess Plateau Restoration Project. As you can see, the before and after, what it took about 20 years to restore a lot of this land, and the central themes around what they focused on was water and soil conservation. So it's a really great success story of that being done at a community scale in this entire watershed region, to restore the soil and the water and the vegetation and the farmland and the communities. 96% of us living organisms are predominantly hydrogen, carbon, nitrogen, and oxygen. And so thinking about those elements, those things, those nouns, and nesting those in a larger kind of process, a cycle, we can look at the carbon cycle, the hydrogen cycle, the oxygen cycle, and the nitrogen cycle, and how those relate and translate into water conservation and soil conservation. So we get energy flowing coming in. You could look at it as like the sunlight coming in from the sun to earth that flows in. Matter interacts with that energy, and they cycles carbon, water, nutrients, all that cycles through our planetary system. And then life interacts with that and webs with it and creates various patterns. We're going to see how we can use this framework to guide us in how we can conserve water and soil. Each one of those elements moves through a cycle, a planetary cycle, the water cycle, the carbon cycle, the oxygen cycle, the nitrogen cycle. And our game as agroecologists and folks interested in just restoring and regenerating land and food and soil, it's good to work within this pattern and learn how these cycles work. Sustainability in this context, water and soil conservation, is fundamentally about our humans' ability to sustain the cycles that sustain us. So it's helpful to begin to see water and soil as flows, as cycles that move through our landscape. And as agroecologists, what the main driver objective we can try to harness is to find ways in which we can slow down the flow of water and soil as it enters our system, spread those out throughout the landscape, and sink them in the ground as long as possible. So the phrase here is slow it, spread it, sink it. So we're trying to slow carbon, spread it out, sink it in. We're trying to slow water, spread it out, and sink it in the ground. So this is an image by a friend, Brock Dolman of the Water Institute at the Occidental Arts and Ecology Center. And he created this image around the conservation hydrology, and highlights the 4 R's of conservation hydrology, which is the pattern in which water moves in the water cycle. It starts off and it releases. You get evaporation coming off the ocean, sunlight hits that energy, it causes the evaporation, you get dense, moist air, moves through the atmosphere, and it eventually will dense and condense and turn into some form of precipitation, fog, rain, or snow. It'll then fall, the landscape receives it, and then our goal is to try to do our best to recharge it in the soil, retain it as long as possible before it then is re-released out and the cycle continues. So this is part of that, like really understanding this as a cycle. And our game is to try to have the water and soil reside as much as possible in these last 2 R's, the recharge and the retain phase. So this is an example of a variety of techniques. And the way I kind of frame this is it's techniques that are stacked in space for redundancy. This is what we call planned redundancy, where water is going to enter this system through rainfall. And we are trying to design as many elements or features or techniques that actually slow that water down, spread it in the ground, sink it as long as possible before it exits the system. So up at the top here, you see that there's a little tractor here called a keyline plow, which just creates a little crevice in the ground, which slows water down as it infiltrates, spreads it out laterally. Whatever runoff excess from that comes, it moves further down slope and it hits this secondary feature, which is called a swale. It slows down, it spreads out and it sinks into that. And then when that peaks, when there's an overflow of volume of water, it goes down what's called a spillway and then enters the second system and fills the second system. So you can imagine these things as sort of these literal, like linear long lakes or ponds that are temporary. They soak in and then they kind of disappear after a day or so of a big rain event. This is a cross section just so you can understand the concept of a swale. Swale is what we refer to as a water harvesting ditch on contour, meaning that it's level, it's dead level and flat. So the cross section of the black line here that I'm pointing out with the cursor is what the slope of the landscape looked like prior to the excavation of this swale. And then you take out a little cut into this ditch and you build a berm with the surplus soil. And then what that does is it allows water to be hit this area, fill in, soak in, and recharge the water table below it. And you can plant on the berms. So you can do like different food production and trees and different things. And it's a really great technique to increase water holding capacity and also grow vegetation. Now that you have that idea of what a swale is, the entry point of this system is here when there's a surplus volume of water and it enters this sediment basin or rain garden, simply just a depression. You could imagine like a bowl, and that fills up until it peaks. You imagine like the bowl fills up and then it spills over the rim of the bowl. Well, there's an actual designated location in which the water then goes laterally out to this upper swale, this water harvesting ditch on contour, this ditch and berm, and that fills up, and then it comes back down over to this lower point, which is a spillway, fills over that, falls into the second rain garden sediment basin, and then runs out laterally again to a second feature, another water harvesting ditch on contour, before it cuts through a culvert pipe underneath this road and into a final sediment basin. This idea of planned redundancy and stacking functions, where we have all these features, all these elements that are helping water infiltrate into the ground. It hits many of them before it exits the system. So essentially, if this water moves through and is utilized multiple times for multiple things, you're maximizing the use of that water. And the idea with this is that this is what we call integration of water harvesting techniques, these little basins, these swales, these berms. This helps rehydrate the soil, which then improves soil structure, which then supports the plants to grow more successfully. And that's what you're seeing here, these elderberries, it's all planted with native plants that are culturally relevant plants used by the southern Miwok and Ohlone people of this region. You can see what that looks like during a rain event to kind of imagine how that water flows through that. So up here at the top is a big greenhouse, 3,000 square feet of greenhouse, and the gutter is actually redirected underground and comes out right about at this point where you're going to see water flowing in just a moment. Up here on the right, you can see the upper field where the tractor did those initial rips of the keyline plow. Here's the water moving down. It's channelizing the water to be strategically pointed into this initial basin. If you recall in the previous slides, this is that sediment basin, the original rain garden, and then it runs out laterally along that swale. Here's the berm with the elderberry grown on top. See here, it's covered in all these grasses and vegetation. There's a second swale, that initial spillway that allows the water to passively spill over into the next feature without causing erosion, conserving soil, and then finally fills up into that lower depression here, which you'll see the culvert pipe there that goes underneath the roadway, across and into this final sediment basin and rain garden that helps support the redwoods that are planted on the edge. Water and soil are intimately related in their success. One way in which that plays out is if you can increase soil organic matter, you can increase by 1% of soil organic matter, you can increase the water holding capacity of 1 acre, 25,000 gallons. This is an example of what's called a biointensive garden in Veracruz, Mexico, called Las Cañadas. And they have agricultural soils, the soils that are used here in cultivation, were anywhere between 5 and 15% soil organic matter. On average, industrial monoculture agriculture has a maximum of 1% soil organic matter. So this is an incredible amount more of organic matter in their soils, which can translate into between 125,000 and 375 gallons of water stored per acre in that soil increase because of the organic matter. So up here on the top left, you'll see a little plot of a garden bed. And the first step is to basically top dress it with a few inches of compost that will then be incorporated into the lower layers. The second step is you dig out your first trench or depression. That's going to be the depth and width of a shovel or a spade. You remove that first layer. You're going to stockpile it in a wheelbarrow at the far end of the bed. That's going to be incorporated at the end. The next step is taking a little fork and forking the lower 12 inches in that next depression below, which then gives you the initial 12 inches of the spade, and then loosening up the 12 inches by the fork. So now you're getting 24 inches of increased soil structure. That's going to have more airspace, more pore space, organic matter for roots to establish. And then the fourth step is you basically turn the next sequence over into the previous one and start and repeat the process until you've created the entire bed from start to finish with this 24-inch depth. This technique allows us to plant more densely, where you can see here on the right, traditional method to row crop would be in these linear rows like this, where you have a lot of space in between. And in this form of agriculture, it's planted on a triangle pattern, as you can see up the top here. So you get better water retention, better yields, less competition from weeds, all in a smaller space. We're trying to have 100% cover of the soil 100% of the time. Ideally no-till or low-till agriculture, so you don't damage that great structure that has been developed. Crop rotation is really great for pest reduction and nutrient retention. You move different families in the same garden plot, they're not as prone to get infested by the same pests. Applying compost and mulch, just recycling of organic matter. Incorporation of nitrogen fixing cover crops, whether they're annuals or perennials, is a great way to tap into that nitrogen cycle and get free nitrogen from the air. Try to incorporate water harvesting techniques where appropriate and possible. Try to shift from annual to perennial crops. These are just the references from the slides today. If you want to reach out and get in touch, contact me here, my emails, and some of the projects I'm a part of. Thanks for tuning in, and I look forward to connecting with folks.